Okay, next, heat of precipitation, we study them based on experiment. For this chapter, you must read all the activities, all the experiments. Okay, now how they do this experiment? It's simple. You just take two different soluble solution and then you will get the precipitate. So later I want you to read all the procedure, understand how to write a procedure. Okay, after you mix this both solution, you mix these two solution and you stir them. You must first get their initial temperature and then you must get the highest temperature obtained. Okay, now how do you do the calculation? I explain again. The first thing you need to do is you take an average initial temperature because you are using two different solutions. You take the average first. Then what you do is you find the rise in temperature because you're going to find your theta, the changes in temperature. Just take a bigger value minus the smaller value. You get your answer already. Okay, next you're going to find the heat energy release. The heat energy release, whereby your formula here is this. Okay, so your mass of the solution. Your mass of the solution is, because you see here, you use 25 centimeter, 25 centimeter. Your total mass of solution is 50 centimeter cube, right? So that's why here is 25 plus 25. And then C, specific heat capacity, just use the specific heat capacity of water, which is 4.2, rise in temperature. You get your answer. Your answer is always in joule. After that, you change it to kilojoule, where you divide by 1000. Okay, now you need to know, for this amount of heat energy release, what is the number of moles used? What is the number of moles used? Because you must understand, in experiment they don't use exactly 1.0 mole. No, 1.0 mole is actually a lot. It's not small. Don't think just because it's one is little bit. No, 1.0 mole, it's a lot of reactant, too much of reactant. So they actually use a very less amount. We need to find what is the number of mole that is used in the experiment. How we find the number of mole? Can you see here they give you 25 and 0.5. So from here you can find N is equals to mV over 1000, right? Because M is the molarity, V is the 25 and then 1000. And you must find for both. Why I must find for both is, the reason is because you want to see is if any of the reactant is a limiting reactant. If both same value means there is no limiting reactant. If one value is lesser means there is a limiting reactant. I will give you the examples later. Okay, I'll teach you later. So when I calculate for silver ion and for chloride ion, I notice both is actually the same number of moles. So no problem. So now I know that 0.735 kilojoule this is only actually for 0.125 mole. So if for 1.0 mole, what's the value? What should I do? I will divide. That's why over here 0.735 divide by 0.0125, I get this much of heat energy. And over here you must write a negative value because this is a heat energy release. There's a rise in temperature. Okay, you see how they write the thermochemical equation. This is your full chemical equation. This is your ionic equation. When you write thermochemical equation, usually you write a full equation. You want to write ionic equation is also correct, but usually it's a full equation followed by the semicolon sign, and then followed by, you have to write this and you have to write all of this. Must have unit, must have the negative sign. So now you're trying to say that when 1 mole of silver nitrate solution react with 1 mole of sodium chloride, it produces 1 mole of silver chloride, 1 mole of this. The heat energy released for 1 mole is this. Okay, can? Right? Okay, next. Now, the next point you must understand is, this one is the value that we calculate from experiment. So this is experimental value. But when you compare with theoretical value, theoretical means is based on theory, is based where all the situation, the conditions are so perfect, whereby there is no heat energy loss to the surrounding. But in real life, not like that. the moment you do the experiment under the aircon, definitely the reading will go wrong. The moment you mix the solution so slowly, heat already released already, definitely reading will go wrong. The moment by the time you talk to your friend and you put the thermometer down into the solution, the heat already released already, so the reading is going to be wrong. So experimental value is always lesser than theoretical value. Actually it's supposed to release this much. Why in experiment the value is lesser? Why? Okay, you see this, when they are calculating theoretical value, they assume that there is no loss of heat to the surrounding, that the plastic thermometer or any apparatus does not absorb heat. Okay, that's the reason why theoretical value is higher. Experiment value is lesser because heat energy is lost to the surrounding. Okay, point number 6 is very important. Highlight everything in point number 6. Every year confirm they will ask you, whereby in order to prevent, we already know heat is being lost to the surrounding, right? So to prevent the heat loss to the surrounding, what are the precautionary steps for the experiment? Plastic cup, polythene cup or polystyrene cups are used because plastic are poor conductors of heat. You don't use a metal, you don't use a beaker because they all can conduct it. Although yes, beaker is a glass, but it's better to use plastic because it's a really poor conductor of heat. The thermometer must be placed into the solution few minutes, then you record the reading so that it have enough of time to record the uniform temperature. The solution, when you mix, you must mix it very quickly so that the reaction can be completed in a very short time. Because like for example, when you're mixing a Milo, okay, or any hot drink, you want to do it before the hot water become cold. If not, it won't taste nice, right? You cannot mix it, right? The same way, you want to do the reaction quickly because you don't want the heat energy to be lost to the surrounding. The reaction mixture in the plastic cup must be stirred slowly. Why you must stir it? So that you get a uniform temperature. The thermometer should not be taken out when you're reading, because the moment you take out, it will be affected. Okay, the thermometer reading should be observed throughout the reaction so that the highest temperature can be obtained. Because sometimes when you are measuring, if you're looking left, right, talking to your friends, you don't realize maybe the temperature already rise up, you take a wrong reading. Okay, now if they ask you to draw energy level diagram, how must you draw? You already learned about this. You can either use ionic or you use the chemical equation. You write your value and you look at all this. Just look at all the details. That's how you draw energy level diagram. Okay, Ken? So that's how you calculate for heat of precipitation. Now here there is another example. I want you to study these examples by yourself. Okay, but before I end this, look at this part. If potassium chloride solution is used to replace the sodium chloride solution in activity 4.42. Okay, so here I think they use sodium chloride, right? Now here they use potassium chloride. So they are asking you whether the heat of precipitation, will there be changes or not? No. Why no changes? Because this potassium or sodium, they do not take part in the reaction. They are just spectator ion. They are just spectator ion. Unless here you use maybe barium chloride, then yes, it will affect the reaction. But these two are spectator ion, so they don't involve in the reaction. They do not cause any changes. Okay, can go through this. Now just as a recap, you must know the definition of heat of precipitation. If they ask you to write thermochemical equation, this is how you write a thermochemical equation. This is how you draw energy level diagram. And if you want to calculate heat of precipitation, remember this is for 1.0 mole. But when doing the experiment or the calculation, they don't use 1.0 mole. So what you have to do is you find first this, and then you also find the number of moles. Then you divide the answer and you get for 1.0 mole. Okay, Ken?